Hello and welcome everyone to experiment number 2. In this experiment, we are going to investigate the motion that we call simple harmonic motion. The motion that we call simple harmonic motion. So actually in this experiment, we are going to divide this experiment into 2 parts. So we are going to have part 1 and we are going to have part 2. In part number 1, we are going to investigate what we call Hooke's law. We are going to investigate Hooke's law, and in the second experiment, we are going to investigate the period of the oscillation, of this simple harmonic motion. In both parts, what we are going to find, we want to find what we call it spring constant K. So in both parts, we are going to find the spring constant of this spring here, So let's look at the theory. In the first part, we are going to investigate Hooke's law, as I told you. And what is Hooke's law? Hooke's law says that within the limit of proportionality, the spring will obey Hooke's law. And that means if I've got a spring and then I applied the external force F. So I've got a spring like this. And then I apply the external force F. What happened is, well, we all know that the spring is going to stretch. And we know that the extension. So this is the original length of the spring. So this is the original length of the spring. Let's call it H naught. And when we apply the force F, what's going to happen? We all know that the spring is going to stretch out. And now the new length of the spring, is x, and we call that the extension. The extension of the spring is x minus x naught, and this is the extension of the spring. Hooke's law says that this extension is linearly proportional to f. So we know that within the limit of proportionality, the external force or the applied force F is linearly proportional to the extension. Let's call this extension with a variable. let's call it E. So we know that F will be equal to a spring constant K, which is the proportionality constant times E. F equal to KE. And this is Hooke's law. And this is Hooke's law. So how are we going to do the first experiment? So in this experiment, you are given a stand, you are given a spring, so you put a spring on top like this, and then you've got a place holder. You've got a place holder. You must be very careful. You must be very careful when you make a reading of the length of this spring here, because the scale here is very far from this. So you might use a ruler to help you to read the scale. And what we are going to do in the first experiment, we are going to put the mass onto the place holder. So I put 100 gram of mass, and then I'm going to read the length of the spring. Then I record this, and then I put the second one and wait until it stops, and then I record the reading. And then I put the third one, the spring is going to extend more, and then I'm going to measure the new length of the spring, and then I put the fourth one, and then I record the new reading of the spring, and again I put the last one. And then I record the new reading of the length of the spring. So now on your table, you would have this is the force, and this is the length of the string. And what we have here, you have 100 gram, 200 gram, and you make it as far as to 500 gram. And then we make a record of the length of the spring, x1, x2, and then x3. And from the theory, we know that F equal to K times the extension. And the extension is x minus x0. So what we have here, we have kx minus k times x0. And then I'm going to compare this equation to y, to the equation y equal to mx plus c. Y equal to mx plus c. And you see that because the way I'm going to record it, this is my dependent variable, and this f, which is mg, this is my independent variable. Normally this dependent variable is y, means the y-axis, and this independent variable is in the x-axis. So what I'm going to do, I'm going to rearrange a little bit. I'm going to rearrange this equation a little bit so that I've got x equal to f plus k x naught divided by k. So I'm going to have this equation. And because this x, the length of the spring, means the dependent variable, so I match this x with y, and then I match this independent variable f with the x-axis. So what does this mean? It means that the slope of this graph is 1 over k, 1 over spring constant. And the y-intercept, or c, means the original length of the spring. So if I plot the graph, I would plot f against x, the length of the spring, and what I would expect a straight line which cut the y-axis at x naught, and the slope is given by 1 over k, and the slope is given by 1 over k. So this is what I would expect in the first part of the experiment. Now we are going to move on to part number 2 of this experiment. In part number 2, we are going to investigate the oscillation of this simple harmonic motion. So as we know, if I've got a spring, so I hang a mass m onto a spring whose spring constant is k, I know that the period of the oscillation t, or the big T, is given by 2 pi square root MOK. 2 pi square root MOK. 2 pi square root MOK. In this experiment, we are going to time the period of the oscillation. So what we are going to do, so we've got a stand, we've got a placeholder, you put one mass in, a mass of 100 grams in, and then you use this stopwatch. What we do, we extend the spring a little bit. Oh, you must be very careful. We extend the spring a little bit, and then I'm going to time the period of the oscillation. You see that it oscillates very quick, so the way to time it, well, this is my technique. I have to swing my hand such that it oscillates at the same period or at the same frequency as this system. When you have only one mass, it's very hard. But you see, if I put more mass in, it is easier because this oscillation will get slower. This oscillation will get slower. You time it such that it oscillates 10 times. So you get 10 times of the period. And here I've got about 6.437. What I'm going to do, I'm going to divide this number. So 500 grams, the period T is 6.437 seconds. And this is 10 times of the period. So in order to get one period, I'm going to divide this number by 10. By 10. For each set of mass, you have to do this 3 times and you find the average. And you find the average. So you do it for 1 mass, 2 mass, 3 masses, 4 masses, and you've got 5 masses on it. So it means that you have to do all together 15 times. So you do 3 times, you record the time 3 times for each mass, and then we have 5 masses. So we've got to record the times 15 times. 15 times. In this case, this mass M is composed of the mass of this case holder. So let's point MP plus the mass of the spring itself, but we will leave this just a little bit. And what we have the mass of these masses here. So we have M, this M is the mass of one of these. And then don't forget, we have the mass of the spring, let's call it MS. But from the theory, because the spring move together, and you see that the lowest part of the spring will feel no mass, but when we go up the spring, this part of the spring will feel the whole mass of this spring. So we have to find the average, and the average of the mass of this spring will be the total mass divided by 3. So the period of this oscillation T will be equal to 2 pi square root MP M plus MS over 3 divided by K. And then I'm going to rearrange this equation, and you see that this T is the dependent variable. This T is the dependent variable, but this M is the independent variable. So this is X and this is Y. So if I rearrange this equation, I would get T squared equal to 4 pi squared divided by K times M plus 4 pi squared divided by K times mass of case holder. This one is constant, and plus the mass of the spring divided by 3. If I'm comparing this equation to Y equal to mx plus c, this is the independent variable, and this is the dependent variable. So it is clear that the slope is 4 pi squared over k, and the y-intercept or c equals to 4 pi squared over k plus mp over ms over 3. So you see that we can use the slope to calculate the spring constant. And from y-intercept, we can use y-intercept to calculate the sum between the mass of the place holder and the mass of the spring divided by 3. So basically you can measure the mass of this place holder here, you can measure the mass of this spring here, and you can compare these two values to the value that you've got from the y-intercept. think that's it. So I think that's it for experiment number 2. Well, I wish you enjoyed the video.